Good afternoon, ladies and gentlemen. Thank you for joining us. My name is Rima Oueid. I am a commercialization executive in the Office of Technology Transitions at the U.S. Department of Energy. I appreciate you guys joining us today. We want to talk about the considerations for building a quantum economy. That includes everything from ethical considerations to market opportunities, the different industries that will be impacted, and why you should care about this today, even before the entire system has been put together. We'll learn also a little bit more about the timing and what people are thinking and the vision of the future for a quantum economy. My panel includes Carl Williams, who is Deputy Director of Physical Measurement Laboratory at the National Institute of Standards and Technology, NIST. We also have Saikat, Guha, Director for NSF Center for Quantum Networks and Associate Professor of Optical Sciences and Electrical and Computer Engineering and Applied Mathematics at the University of Arizona. We are also here with Matt Langione, a principal at Boston Consulting Group. And last but not least, Celia Merzbacher, Associate Director of Quantum Economic Development Consortium. So with that, I'm going to hand it over to my esteemed panel to go around one by one and tell you a little bit about their background and their connection to helping to build this quantum economy of the future. With that, Carl, would you like to take it away?
Yes. Thank you for the invitation. Good morning, everyone. It is a pleasure to be here. I am an atomic physicist by training. I have been working in the quantum information arena since 2000. In fact, I coordinated all the quantum information activities at NIST since the year 2000. We formally established our program. I established the first interagency working group within the Office of Science and Technology Policy back in the year 2008. So I have been actively engaged in this field for a long time, and under the National Quantum Initiative Act, I also helped establish the Quantum Economic Development Consortium, which you will hear more about later.
Thank you, Carl. Saikat?
Thank you, Rima, for the invitation and the kind introduction. So I'm Saikat Guha. I'm a quantum optics and information theory person by training. And prior to my joining the University of Arizona 3 years ago, I was in Boston for almost 15 years, did my PhD 2008 at MIT, and then I was at BBN Technologies for almost a decade, where we started a group on quantum information processing. My personal interests in this field are in what I call photonic quantum information processing, all sorts of applications where treating light in a quantum mechanical manner can let us give us more insight on where we can do better in terms of performance in communication, sensing, security, simulations, computing, etc., by leveraging quantum mechanical properties. I currently lead a recently awarded center. It's a 10-year engineering research center funded by the National Science Foundation. And my personal interest in this particular topic of today's discussion is that one of the biggest things of our center that is non-technical is a whole research thrust on societal impacts of the quantum internet and quantum technologies. Thank you.
Thank you, Saikat. Matt?
Sure, thanks, Rima. So I'm Matt Langione, a principal at Boston Consulting Group, working across really all areas in the tech sector, but with a special focus on research-inflected deep technologies, or deep tech, as we call it, things like quantum computing, neuromorphic computing, and I'm also a member of the Quantum Economic Development Consortium, where I've been working with Carl and Celia, among others, on scoping and identifying high-value use cases for businesses to pursue. I authored a piece on quantum computing and its potential value to business and society. It's called Where Will Quantum Computers Create Value and When? And that forms the basis for a TED Talk that I've given and that will be released in October of this year. I've addressed audiences on the topic at a number of the major conferences in the field, so Q2B, at IBM's Q Summit, AI World, IEEE, and I'm just delighted to join this group here. Thanks for having me.
Thank you, Matt. Celia?
Hi, Rima. Thank you for the invitation to be part of this panel. I'm Celia Merzbacher. I am Deputy Director of the Quantum Economic Development Consortium. which is a NIST-sponsored and initiated consortium, but it's really an industry-driven group that looks to enable and grow the quantum industry in the US and globally. And our initial efforts are aimed at identifying what the technology needs are to enable quantum applications and to help look for strategies to address the gaps to meeting those needs, including in workforce as well as technological ones. So I'm looking forward very much to talking with the group today about what those gaps are and how we're going to achieve a robust quantum industry in the US.
Wonderful. We'll start with Carl. A targeted question for you. How do you define quantum supremacy, and what do you see as the vision?
So this is a really good question because there's been a lot of discussion and some people say hype around the Google claim that they had achieved quantum supremacy. And this is something that really is not surprising that it's occurred. So quantum supremacy is the ability to do a quantum computation that would take far longer on classical hardware than it will take in the quantum world. And this just has to do with the power of a quantum computer. So it's a remarkable demonstration. There was a lot of discussion afterwards by IBM and others who looked at it and said, well, you know, they could have used a far more efficient classical algorithm. The reality is even where that barrier is, if they just added 3 or 4 more qubits to it, the computation was, again, blown up exponentially, and there'd been no way of ever calculating the result. This has been known for a long time, that if you could build a fully fault-tolerant quantum computer, one that you can correct errors on and therefore can continue to do your calculations, that it would quickly outsurpass the computational power that exists with all the computers in the world. And so not shocking or surprising, the calculation and the computation that Google did was one that has no commercial value. What we're really looking for, and what I will call real quantum supremacy, is when we finally have a calculation that actually has commercial value or value to the broader scientific community that enables something that could not be done any other way. And so we're looking forward to this. This is not something that's going to happen tomorrow, but it is a process, and it is ongoing, and everything else. So I look at the vision of getting to where quantum computers are contributing to our development of science, technology, and industry as being an exciting moment, one that will revolutionize perhaps everything from weather forecasting to drug design to predicting when earthquakes will happen. So this is a great concept. It's one that we really look forward to, and the initial demonstration has been done, but let's watch as the game plays out.
Thank you. Saikat, this really brings up a lot to think about, because it sounds like industries will be transformed. Is now the time to start thinking about how to make quantum technology fair and equitable?
I feel we are at a very interesting cusp in terms of the history of technology. So on the one hand, there's a lot of basic science research that still needs to be done in this field. We are definitely not at a point where we are ready to say that we exactly know what quantum technology is. We are ready to choose our favorite qubit technologies for every single application and build out the network and so forth. But at the same time, we also know several applications that may have some really dramatic consequences and implications on our society and our day-to-day lives. And especially some that may have various ethical and policy issues that are important to start investigating in conjunction with that technology development research right now. So this has been the philosophy behind one of our 4 research thrusts in this ERC that I lead on, called Center for Quantum Networks. So that research thrust is called Societal Impacts of the Quantum Internet. It's led by my colleague, Professor Jane Baumbauer in the College of Law in the University of Arizona. And as one of the first activities that we are going to do starting this year is that Jane is going to run what we are going to call Quantum Society Fellowships. And these will address various important ethical and policy issues that are known and some that may not be even known. just to give you some examples of the kinds of things we are considering there in terms of fairness and equitable, which is the question that you asked. One of the users of a quantum internet will be what we call blind quantum computing in the technical literature, which simplified is basically you and I will be able to access, say, IBM's quantum cloud that just recently demonstrated that supremacy problem that Carl just mentioned, but be able to run our own algorithm on that quantum computer without even, in principle, the owner of that quantum computer, in this case IBM, being able to find out what we just computed on it. Okay. So what type of issues this technology will bring to surface? So so these are one of the kinds of things that, so quantum networking access to quantum computers will, to me, it will democratize the access of quantum computing. Everybody who has access to a quantum internet, even if they don't have access to a quantum computer, will be able to do things, and it will open up a whole new marketplace of new app developers. People will start to innovate without being fearsome of their technology, their ideas being found out by somebody who own the quantum computer. But there's a whole negative side to it, potentially unknown side to it. I shouldn't say negative, that we don't know what that access will potentially bring forth that we cannot anticipate right now. Things like that. There are lots of things that we sort of can see that might be technical, ethical issues, policy issues, but there are many that we cannot.
Anybody else have any other thoughts that they want to chime in on?
Yeah, so let me just add one thing to what Saikat mentioned. So again, one of the things one knows you can do with a quantum computer, if it's fully error correctable and everything else, is to break RSA or most of what we call the public key infrastructure that is necessary for you to do secure transaction on an HTTPS website. Clearly, while stealing some credit card information is great, invading the SWIFT system where we do international banking transactions worth billions of dollars and stealing money there would be horrible to our economy. So this is one of these ethical situations, to kind of put it back into layman's term, where you really don't want it to happen. Now, in the early days, we're not going to have the quantum internet. We're just going to have the quantum computer. And we probably can ensure that nobody's running these kind of algorithms that would basically be being used to do theft. But, in the future, the days that Saikat mentions, we really want to be able to protect against that kind of activity.
Matt, according to Boston Consulting Group, in the coming decades, expected productivity gains by end users of quantum computing in the form of both cost savings and revenue opportunities are expected to surpass $450 billion annually. Gains are expected to accrue to firms and industries with complex simulation and optimization requirements. In light of this, do you consider quantum a disruptive innovation? And if so, which markets will be the most impacted, and how long can legacy companies wait before they can't catch up in the quantum race?
Really, really good question, Rima. So first, let me say that there's a somewhat narrow theory of disruptive innovation as coined and defined by Clayton Christensen. And that may actually not apply to quantum computing because it requires that market-leading firms and value networks be displaced. But let's hold that aside for a moment. If we take the two words, disruption and innovation, separately, both can be applied to quantum computing. So innovation is clear, right? There's this existing paradigm in supercomputing that's been in place for 70 years, a period during which supercomputers have been our arm against challenges ranging from cracking Nazi codes to sequencing the human genome, right? And now, with what's on the table in quantum computing, we're proposing an entirely new paradigm defined by subatomic physical properties that weren't even known to scientists 100 years ago. So I think that you can check the innovation box. Disruption is a little bit trickier. So there are industries in which the value to end users of the technology has the potential to be really extraordinary, especially materials design, drug discovery, financial services, fluid dynamics. And the value to end users in these industries, and by end users here I mean the Pfizers and JP Morgans of the world, the value to end users in terms of net income could reach 150 to 250 billion a year. And then when you spread that across all industries, that's where you got the number that we quoted, the 450 billion, to ranging upward to around 850. I think that was the full range. Now, those numbers kind of are just massive absolute numbers, but to give it a little bit of context, let's dive into the details of pharmaceutical companies. So today, globally, they have about 100 to 150 billion in annual net income. In terms of revenue, it's 10 times that much. With full-scale and fault-tolerant quantum computers, we've projected a potential impact on the scale of $35 to $75 billion. Once things like de novo design of biologics, genomic target identification, and other use cases come into play. So that is value creation on a massive scale by the numbers. But what will be most disruptive, in my view, when we think about pharma, is how companies spend. How much of the traditional R&D budget can go over to computation, for example. And then how they align competitively in a new world where discovery is radically transformed. And that's sort of at the micro level, but then there are macro considerations about how drugs are approved and even brought to market. I mean, in a world with full-scale fault-tolerant computers, you could imagine a place where biologics are replacing small molecules. And then the question then becomes, will we really need the trials and approvals processes that we have in place, at least in the way that we have them in place? Perhaps we will, but we'll have to rethink all of these regulatory processes. I think that those questions that quantum computing invites us to ask is just a reminder that disruption goes far beyond the dollars and will require a lot of coordination among and between businesses and government coordination as well. And I think that a little bit of that is already kind of what's underway. Carl and Celia will and can talk a bit about what's already underway there. And I think we're kind of being very front-footed in the US on these issues. But I guess to answer the question, very, very innovative, very, very disruptive. And it's sort of a separate question about disruptive innovation.
And Matt, just to clarify, how long do you think legacy companies can wait?
Not very long, in my view. And there are a number of reasons for that, and perhaps we can get into it further down the road. But I think in large part, it's because quantum computing is not really one of these kind of engineering challenge-based timeline paradigms where you can sort of predict how long things will take based on how long advances have happened in the past with comparable technologies. It's actually this fundamental science that needs to be aligned on, fundamental questions around the science, which means both that the timeline could be actually quite long, as you say and imply in your question, but that also means that it's a candidate for a real precipitous breakthrough that could come at any time, right? And I think that there's a real danger that companies could be caught flat-footed in a number of different ways. Celia is really articulate around talent and may hopefully have an opportunity to either follow up on this question or address that later. But then there's also things like IP and skills, upskilling. Those aren't things that can just happen overnight. This isn't a DIY technology, needless to say. So with that in mind, for companies in these particular kind of, I would call them high impact fields, I think that the ramp process needs to start basically right now.
Thought you would say that. Thank you. Celia, do you have any follow-ups to that, or I can jump into the next question?
Matt is really on target, and I think a number of the comments have referenced the fact that there are activities taking place at all different parts of the innovation spectrum, from the basic research at universities to fairly product-driven work in certain companies. And we can talk about the different parts of the supply chain, but with that activity happening at all sort of different stages of innovation, the need to coordinate and to feed the workforce so that you have the talent coming in is even more important. It's not just we can sort of sit back and wait for this research to happen at the universities and the people will graduate and they'll go work in the companies and the next step will happen. It's much more in parallel in this case, even though it's still pretty early days. And so the need to have the entire ecosystem in sync, in a sense, or at least aware of what the other parts are doing, is especially important.
Carl, you had a comment?
Yeah, I was just going to go back. I thought Matt's analogies were just spot on. Although, NIST had its first workshop with industry in this area back in 2001. And this is where one of the VPs of one of these companies basically told me, he said, people talk about disruption and innovation, and revolutionary technology. He says, there's only a couple of revolutions every century. This technology is really revolutionary. It's going to change how we do things in such a fundamental way that if you are too late boarding the ship, it will have sailed and your bottom line is going to be impacted.
Celia, QEDC recently released the results of a market forecast for quantum computing. What are one or two key takeaways that you think are important for us to know?
So yes, QEDC commissioned some work by Hyperion Research, which has a lot of experience in the high-performance computing space. And they helped through some surveys to get an initial handle on the size of the quantum computing market and trends in growth over the next 5 years or so. And based on the responses that they got and some back of the envelope estimates, frankly, on what fraction we were surveying and how to sort of translate that into global estimates, they estimated that the current market is somewhere around $350 million annual, and that it's likely to grow roughly 30% compound year over year for the next several years. So by 2024, they estimated that that market would be pushing $1 billion. Now, those numbers are really different from the ones that Matt gave, and that's because we're really talking about now and not looking ahead to the potential so much. And these are probably fairly conservative numbers, frankly. The people that we were talking to were sort of the technical people at the supplier companies and some of the users as well. But again, as we've discussed already, without really being able to anticipate when and in what fields the applications are going to come, it is hard to estimate. The survey also revealed that, not surprisingly, most people believed that access to quantum computing would be via the cloud for the most part initially, and not people buying systems and having them on premises. That may change again at some point in the future. That points to another issue that maybe we'll talk about in this whole economic development area, and that is the size of the market. What is the size for the number of quantum computers that are going to be out there and that will serve the need of the research community in the immediate future, and how quickly will that grow? I think that we are in a point right now where the suppliers don't see the big market. They're not sure when the market is going to grow and how big it will be. So smaller suppliers in particular have very precious resources for R&D, and they're not necessarily going to spend those on something that's somewhat still in the longer time frame for them. So that's an important thing for the government, I think, to address as it thinks about investing not only in the basic research, but in making that supply chain start to work. And so that's an area where the QEDC can help, bringing the suppliers and the people who are going to develop things that are fit for purpose and meant to work in these unusual environments and application spaces, so that, again, the supply chain, it exists, and it exists in the US.
Right. We're going to move into the general questions section. And so, everyone has an opportunity here to raise their hand and ask a question, and then I'll go around and ask some more specific ones. But are we in a quantum race? Where do we stand versus others in the world? Does anybody want to take that?
So yeah, I think there is a race going on. I think many countries have come to realize that this technology is going to be remarkably impactful, much the same way that lasers and electronics were in the 20th century. So there is a race going on, but I think it's a race in which the whole world wins. If you look and you ask who's publishing the most paper in quantum communications, well, at the moment it's the Chinese. If you look at how much venture funding is going on, come back to the US. I think you can look at the strengths and weaknesses of the different parts of the world. What I will point out is that for some of the core underlying technologies, there aren't going to be 20 companies. there will be a few winners. And so everybody's juggling to be a winner. But you know, you don't have to be an Intel to be a winner in the semiconductor industry. The companies that produce the lithography equipment necessary to make that run, most people don't know the name of those companies because they're not commercial household words. And yet, they're absolutely essential to Intel doing its business. So there is a lot of opportunities out there.
Any other thoughts?
I would just say, sorry, to what Carl was just saying, he said that basically it's a race in which everyone wins. I think that couldn't be better stated and couldn't be more timely. I mean, obviously right now, kind of have the specter of COVID-19 upon all of us, which is, like, I think a period of a kind of unprecedented call for scientific and medical, in this case, collaboration across borders. I think quantum computing has so much potential for good, kind of in all of the right industries and verticals, that I think that the onus and the impetus on collaboration is so great that it simply will happen, right? And if you think about the government investments, you have 10 billion across all quantum technologies in China, well, 1.3 or 4 in the US, and then something on that same scale. So around 15 billion overall in government spend between US, Europe, and China. I think that just having papers and things like that behind silos is something that really hasn't happened that much yet. And I think that spirit of collaboration just needs to continue, given just how important the use cases are from a societal, not just a business lens.
Celia?
Yeah, also, I think in this case, and it was alluded to earlier by Carl, there's both the economic competition and then there's the national security considerations as well. And so nations are thinking about both of those considerations when they make investments. The idea that quantum technology can have implications for cryptography and things like that are very important for governments. And so there's sort of these two competing aspects in some sense. And I think on the commercial side, pretty much every company that's in business wants to be a global, sell into the global market. And so there's very strong competition worldwide to access those markets. And then at the same time, governments want to be on the leading edge for national security reasons. So that probably will just make things go even faster, in a sense.
And I would amplify what Carl and Matt just said, that the competition, yes, there is a competition, it's a healthy competition, and that there will be multiple winners. And even in specific areas of quantum technologies, if you look at, say, quantum computing, I mean, there are IBM, Google, Rigetti, BBN, many companies that are working on superconducting-based qubits. And then there are multiple companies working on trapped ion qubit architectures, like IonQ, for example. There are 2 companies, at least, that we know of that are quite big already, working on all photonic quantum computing, PsiQuantum and Xanadu, based in Palo Alto, the other in Toronto. So even though these companies are all currently in a race to build that first fault-tolerant quantum computer of a certain size that can solve problems that are useful, and quantum supreme in the definition of Carl just mentioned, but I personally feel that in the future quantum ecosystem, there might be actually place for these individual technologies.
Let's talk a little bit about some of the potential discoveries. What kind of fundamental discoveries and capabilities could quantum computing, sensing, or networking lead to? And Carl, I'll let you kick this off because this is one of those questions that I was going to target you to, but I'm too tempted to share with everyone.
Yeah, look, I think it's very, very early days, and what's surprising about this is probably the most important impact of this technology has probably not yet even been thought of. Mm-hmm. So what I like to give an example of is something that involves sensing, communications, and computing, because this is one of these kind of interesting problems. And what's a problem I want to do? Something called relativistic geodesy. That is, all objects have natural modes of motions, including the Earth. And you can say, well, why would I care about that? So let me give you an example. I take two of the most sensitive quantum instruments I can build. These are something we call atomic clocks, but they can also be used to determine the relatively height from the center of the Earth. And I put them out along a quantum network and entangle them out along the San Andreas Fault in California. And I watch the stresses build up, and perhaps one day in the future, I'll be able to predict 2 weeks early that worst earthquake that's going to ever hit the US is going to go off. Mm-hmm. And so that's one of these applications of something that we can't do today that is really novel. But everything from going to do black holes compute, which you have professors talking about, to everything else. So the fundamental discoveries in nature are also likely to come from the same technology. So it is absolutely exciting, both from understanding the universe to saving humanity and everything else that Matt and the others have talked about. So I just think it is really exciting, and I don't think we have a clue what the most important application will be.
I think, Carl, that's just really inspiring and well put. I think when I think about quantum computing, the interesting thing about it is that it's not actually that it does that many things. Like, it's not a general purpose computer that has all of these different problems that it solves. I mean, this is probably going to be too reductive, but it's almost like there are these a few archetypes, like combinatorial optimization, differential equations, linear algebra, and factorization. But the thing is, and this is what Carl was alluding to, that small base of problems, of problem archetypes actually expands onto an enormous set of potential use cases. And I agree with Carl that, like, there are a number of things that we can scope. I think, curiously, when you notice the things that have been scoped, they're things that are important to material scientists and chemists, who are precisely the people that study qubits and experiment with them. So I think that alone tells you that when this is more broadly accessible and applicable and studied around industries, you'll find a great kind of efflorescence of potential use cases. One that I love is this. If you think about fertilizer production, which is kind of one of these hallmark problems of in the science of climate change, the way that most fertilizers produced today is by fusing nitrogen and hydrogen to make ammonia, which is the active ingredient. It's called the Haber-Bosch process. And it works, but only at an extraordinarily severe cost, both for companies that spend $100 to $300 billion every year, and for the environment. We estimate that 3 to 5% of the world's natural gas is expended annually on fertilizer synthesis. So you might ask, okay, well, why have scientists failed to develop a more efficient process? First of all, the Haber process is a miracle of science in and of itself, so no criticisms. But the reason is that in order to do so, they have to simulate the maze-like molecular interactions that make up the electrostatic field of the key catalyst, which is nitrogenase. Now, scientists effectively know how to simulate nitrogenase today, but the problem is that it would take 800,000 years on the most powerful supercomputer we have. And that's the sort of thing, like with a full-scale quantum computer, it could take less than 24 hours, right? And so it's just thinking about discovery on that scale and the idea of kind of unlocking something that's so valuable both for companies and for the environment, which is, I think, what keys some of the talk that Carl, Celia, Saikat, and I were having about kind of the public good and the benefit to the world of a technology like this.
Let's talk a little bit more about companies and there are many problems that today's computers cannot solve. Some simply wait till the next generation of semiconductors comes along, rounding out the bend on the assembly line. Others will remain beyond the reach of classical computers forever. What is beyond the reach of forever? Anyone want to take that?
You've now probably asked the most difficult questions. So we understand that there are problems that a quantum computer can solve, and we also believe there are problems it will never be able to solve. But to say that doesn't always quite answer the question, because a classical computer cannot solve optimization problems exactly, not complex real-life ones. However, they can do damn well at it. So the question remains difficult, because, well, what kind of approximate solution can I come up with? How good can that approximate solution be? And then there are the really very fundamental theoretical things that people like John Preskill and others like to ask. And that is, well, how does the universe compute? Is it based on the standard model of quantum that describes the universe as we know it? Well, we know that that model isn't quite complete because it doesn't explain gravity. So it is possible that using quantum gravity, whatever that theory should end up being, one could use that technology to build yet even a more powerful computer. So this question it has so many layers to it, is a wonderful question, but I don't think there's a simple answer to it. And you know, this is part of the fun of this both being a science and engineering and a technology that Matt and everybody else has talked to. We've already talked about the impact of this, but the reality is it is also about discovery at the foundation of what we understand about our universe.
And Carl, I think the other thing, and Rima, the other thing that kind of, I think, makes this an interesting question, or one thing that surfaces by the light of this question, is that you have this effective rising tide of advances in classic computing that you always have to kind of overcome when you think about quantum advantage in the industry perspective, right? So it always has to overcome advantages that are already happening in, you know, deep learning and in other forms of classical computation, right? And that's just something that I think there's a lot of theoretical work, right, around coming up with algorithms and then disproving them as, you know, quantum advantage, things like that. So it's just it's a really fertile field, and one that I think the dynamism of that field is partly this interchange between what classical computers can do and what quantum computers can do uniquely.
I think another point, while you know the discussion right now is between A or B, the answer is going to be A and B for at least a while, probably, because quantum computers aren't maybe that capable for general purpose problems that classical computers are really good at. And so coming up with algorithms that allow you to parse a problem and do a sort of mixed approach where you take advantage of the strengths of each is likely to be maybe the answer for a while.
Yep, and something I would like tie back to what Carl mentioned some time back about how there has been this race between classical and quantum solutions to the same problem. Mm-hmm. If you look at these sampling problems, boson sampling, IQP, and all these problems that many of these companies are trying to get towards to show quantum supremacy, interestingly enough, some of those problems, there's no way computer science community would have even considered looking at those specific sampling problems had it not been for the case that those problems happen to be easy for quantum computers. So there has been innovation also on the classical computing and classical algorithm side that was initiated by these discoveries.
Thank you for that, Saikat. So just to wrap up, I would like to get everyone's parting thoughts, and you also have the option to answer what efforts are underway to coordinate US efforts to build a quantum economy. So any parting thoughts, things that you want companies to consider, or, you know, other thoughts? I'll start with Carl.
So I think a lot is going on. I think the QEDC is crucial to helping educate companies and to bring people to the table. I think the Boston Consulting Group is. I think academics are. I think that the most important thing is that for those people who want to know, to reach out and to find an appropriate venue to be educated. And so Matt has talked on this and everything else. I think it's an exciting time. I think it will evolve slowly, but I also think that those companies who think that they can wrap their hands around this one in a very short period of time, when it hits a certain threshold, they're going to be shocked and surprised because they aren't going to understand the impact of this potential technology on their bottom line. So engage, have a great time, fun. It's really an exciting period.
Thank you.
And I guess I would just agree. I think that leaders should worry less about quantum computers arriving too late and more about them arriving too soon, before they've had the chance to make the necessary preparations. I think, to kind of mangle a quote from one Nobel Prize winning physicist, quantum computers are more different from current computers than current computers are from the abacus. And when you think about that, it'll take time to really make the necessary workflow integrations to onboard talent. And really, I think an underestimated factor is that it'll take time and vision and imagination to identify and scope these high value problems for businesses to tackle. I don't think that you'll just be able to buy your way into this once the technology matures. I think there'll be real rewards in terms of IP and talent and skills for early movers. And so I think companies should be asking what they can do to get ready now.
Thank you.
Carl and Matt already covered the important points from the industry perspective. I'll just say from the perspective of the academia, it will be really, really important for us to start thinking very carefully as to how do you teach quantum information sciences. And there is a workshop that I attended that was organized by the Kavli Foundation 2019. 35 universities were represented there who are considering rolling out programs in QEDC, a new discipline called quantum information science and engineering. So what should that discipline even look like? There be aspects of computer science, electrical engineering, material science, physics. What should we teach? How do we train students that are who are not only capable of getting injected into the current industry as we envision it, but also be able to fundamentally think in new ways that we trained in the conventional way cannot? I mean, it's a very hard question. I mean, how can we create a workforce that can intuit in qubits and entanglement in new ways that we ourselves cannot? And that will be very, very important to create that workforce that can not only be injected into the current industry, but grow new ones and create new ones. And we are also very, very closely working with Celia's group, QEDC, on figuring out what an industry retraining / certificate program should look like. And I'm really looking forward to seeing how that rolls out.
DOE is also involved in QEDC, and we're very grateful to Celia's group and to NIST, Carl, for setting that up. Celia, you get the last word. So last but not least.
Well, thank you. And obviously, everybody who's on this panel knows about QEDC and is involved, but it's very much inclusive and open. So if people are interested in learning more, I'll just put in a plug for going to our website, quantumconsortium.org, where you can find out more information or connect with us directly. I will, at the end here, I guess, go up 100,000 feet and remind everyone that while we've spent most of today talking about quantum computing, there are many other applications of quantum science and technology. And some of those are going to be here much sooner, and maybe will be sort of the step along the way to solving some of the problems that are going to have to be solved to make quantum computing real. So, and also, so that sort of is the vertical spread. There's also jobs for people who understand electronics and RF engineering and microwave technologies and all kinds of related fields that they need to get a little bit of quantum knowledge in order to be able to sort of enter and succeed. But there's a broad swath of skills and knowledge that is needed. And so if someone's interested, they should definitely go and talk to folks at their local university or go online and just educate themselves to learn more, because there's a huge scope of the technologies that are going to be needed in order to make the science that's coming out of all of the research today into really practical and useful technologies.
Thank you for that, Celia. Yes, there are many the market use cases, I think, were evidence of how there's a need for more work to be done, not just in the computing side, but the sensing side and the networking side, because there are certain use cases that just don't work if the network looks only one way. And so I encourage folks to take a look at a series of webinars that DOE recently also did that explored these market use cases in life sciences, financial services, as well as global communications, transport, and navigation. So we're at our time. Thank you all. Greatly appreciate your participation, and we look forward to answering questions in the chat. So with that, have a wonderful afternoon. Goodbye.